What's up, AP Physics, C Electricity and Magnetism students? Welcome back to our Elegant Physics videos. Today's topic 11.8 RC Circuit, Part 1. So let's jump right in. So let's recall that capacitor, two nearby surfaces of equal and opposite charge, and it has the ability to store energy. The form of this energy is electrical potential energy. Connecting a capacitor to a battery produce a simple circuit. Now, since the capacitor here in this case is in parallel with the battery, since we have two terminals in common between the capacitor and the battery, then the potential difference across the battery will be equal to the potential difference across the capacitor. The charge on the capacitor is defined to be the charge on the positive plate. Since this plate, the upper plate, is connected to the positive terminal of the battery, then this will gain positive charge. And for this plate, the one that is connected to the negative terminal of the battery will become negatively charged. So the charge that we will be able to calculate using this formula is the charge on the positive plate, and by default, the charge on the negative plate will be minus Q. However, in the questions and practices, whenever they ask you to find the charge on the plate, it's enough to show the charge on the positive plate. Now, the magnitude of the uniform electric field within the capacitor is given by this expression. E is equal the charge over epsilon 0, which is the absolute permittivity, times the area of the plate. Now, the thing is, since we will have one plate with a positive charge and the other plate with a negative charge, an electric field will be produced from the positive plate to the negative plate. Now, the capacitors separate charges, and this separation leads to potential energy stored. Now, to find the energy stored by any capacitor, it's enough to use one of these expressions. So we have three expressions can be used to calculate the potential energy stored in the capacitor. So have CV squared, where C is the capacitance of the capacitor, and V is the potential difference across the capacitor, where Q is the charge carried by the capacitor. Now we can define the energy density U. This is lowercase u, which is equal to energy per unit volume. So it's the potential energy that we found it in the previous expressions over the volume of the capacitor. Now, to find the volume of the capacitor, we just need to multiply area times distance, where the area is the area of the plate and the distance is the distance separation between the two plates. So the U is equal half C V squared over A times D. Here we can simply write U equals half C, and the V squared can be written as V times V over 80. Now, since E equals Q over epsilon 0A, then E times epsilon 0 is equal Q over A. And also we know that Q equals C times V. So we can change C times V with Q, and Q over A, it can be written as E times epsilon 0, so half E times epsilon 0 multiplied by V over D. Now V over D also it can be written as E. Now E times E is E squared, and we will be able to get this expression. Now capacitors in series. Two capacitors are connected in series. Both capacitors are initially uncharged. Now recall that to connect two electrical elements in series, you should connect them, or they must have one terminal in common. So this capacitor and this capacitor are connected in series. When a constant positive potential difference VAC is applied between the points A and C, as we can see here, so if we apply potential difference across these two capacitors, the capacitors becomes charged. The total voltage is divided across the capacitors, allowing the circuit to handle higher voltages, with the largest voltage drop occurring across the smallest capacitor. Now, because that the potential difference across the capacitor, it can be written as Q over C. So the higher the capacitance, the lower the voltage will be. So whenever we have applied a potential difference VAC, and let's assume this capacitor here is larger, then the potential difference here will be less. So we can deduce that the VBC is less than the VAB in case the capacitor 2 is greater than the capacitor 1. However, the electric charge in each one of these capacitors is the same, and the reason is after we apply the potential difference, this plate, or let's say, becomes positively charged. A similar amount of charge but with negative sign will be in the opposite plate, and also here we will have the same amount of positive charge facing this plate, and the same amount of negative charge will be facing the last plate. So we can say that the electric charge in this system will be the same across the first capacitor and the second capacitor, and this has happened whenever we have connected the capacitors in series. Capacitors in series all have the same current flowing through them, so I equals I1, I2. Therefore, each capacitor will store the same amount of electrical charge on its plates regardless of its capacitance. This is because the charge stored by a plate of any one capacitor must have come from the plate of the adjacent, or if it's adjacent capacitor. Therefore, capacitors connected in series must have the same charge. So Q is equal Q1 equals to Q2. So as a result, for capacitors connected in series, each capacitor carries the same magnitude of charge, and the total potential difference is divided across the capacitor. So for simplicity, I can write that Q1 equals to Q2, but the VAB doesn't necessary to be equal to VBC. However, the addition will be equal always to the total potential difference across the two capacitors, or the capacitors that are connected in series. Now let's find out how we can calculate or find an expression for the capacitor, the equivalent capacitance in a series combination. We know that the VAC is equal VAB plus VBC. Now our target is to reduce this electric circuit into one singular capacitor. This capacitor will have the same electric potential difference across the two capacitors, and the potential difference, the total potential difference, will be AC. So this is VAC, or the C equivalent, and the charge across the two capacitors will be the same as the charge in the C equivalent. So let's write that the charge across the first capacitor, let's call it Q1, and here Q2, and this is a Q equivalent. Now the thing is, since they are in series, then Q1 should be equal to Q2, and also the Q on the equivalent capacitor should be the same, so equals to Q equivalent, and let's denote it by Q. So VAC equals Q over C, VAB is Q over C1, VBC is Q over C2. Now we can cancel Q with the Q after we take the Q as a common factor, and we will end with this expression that allows us to find the equivalent capacitance. For I capacitors are connected in series, the capacitance of the equivalent capacitor is given by 1 over C equivalent is equal the summation of 1 over Ci equals 1 over C1 plus 1 over C2 plus 1 over C3, and so on. But remember that this formula will help me to find the reciprocal of the equivalent capacitance. To find the equivalent capacitance, we should flip the answer upside down. Now, so we can say that the reciprocal of the equivalent capacitance of a series combination equals the sum of the reciprocals of the individual capacitance. In a series connection, the equivalent capacitance is always less than any individual capacitance, and the magnitude of the charge is the same on all plates of all capacitors in series combination as well as in the equivalent one. The potential difference of the individual capacitors add to give the total potential difference across the series combination. So whatever the total potential difference here across the two capacitors, it will be the same as or for the equivalent capacitor. Now for I capacitors, let me remind you with the formula that it will be provided in the equation sheet. And remember that always the equivalent capacitance is smaller than the individual. Now some shortcut equations for capacitors in series. The shortcut one, if you have I capacitors in series, you can directly find the C equivalent by using this expression. Now shortcut 2, if you have two capacitors in series, you can use C equivalent is equal C1 times C2 over C1 plus C2. And remember that we cannot use this formula unless we have only and only two capacitors, so it doesn't work for more than two capacitors. And for shortcut 3, if you have capacitors of the same capacitance, which means they are identical and in series, so we can say that the C equivalent is equal C over N. So the value of the capacitance over the number of capacitors. Now these shortcuts are the same shortcuts that we used for resistors when the resistors are connected in parallel. Now here we use the same shortcut, but now the capacitors will be connected in series. Now capacitors in parallel, two capacitors are connected in parallel. Both capacitors are initially uncharged. So there is no charge in any of these capacitors and they are connected in parallel because we have two terminals in common between the two capacitors. When a constant positive potential difference VAB is applied between A and B, the capacitors become charged. And the same potential difference will be here and there because they are connected in parallel. Hence, in parallel connection, the potential difference for all individual capacitors is the same and is equal to the VAB equals V. The charge Q1 and Q2 are not necessarily equal. However, since the charge can reach each capacitor independently from the source, such as a battery, for example, of the voltage VAB, the charge R, Q1 should be written as C1 times V. So for higher capacitance, you should expect to have higher charge because the voltage is the same in both capacitors. And the total charge of the combination should be written as Q is equal Q1 plus Q2, and this is exactly the charge that we will find in the equivalent capacitor. So after we turn this into one singular capacitor, the capacitance is the equivalent capacitance, and we will see how we can find its equivalent in the next slide. The potential difference will be the same as the one in the two capacitors in parallel, so the same potential difference, but the charge here, it's a Q which is equal to Q1 plus Q2. So the equivalent capacitor will be able to store more charge than the individual. So for capacitors connected in parallel, the potential difference across each capacitor is the same, and the total charge stored in the combination equals to the sum of the charges on the individual. Now the equivalent capacitance C equivalent of parallel combination is given by, we know that they will carry the same charge. Now we can write C equals Q over V, which means Q is equal C times V. So Q here represent the charge in the equivalent, Q1 the charge in the first capacitor, and Q2 the charge in the second capacitor. And Q equals CV, which is equal C1V plus C2V. And I use the same letter V in left hand side and right hand side because the same potential difference will be applied on the parallel combination as well as in the equivalent. Now if we took the V as a common factor, we can cancel the V, and the C equivalent in parallel combination, it should be written as C equals C1 plus C2, which is not the same as the equivalent resistance, because in the equivalent resistance we use 1 over R equals 1 over R1 plus 1 over R2. So in summary, for capacitor and resistor, the equivalent in series for the capacitor, it will be 1 over C, or let me write it down, C equals 1 over C1 plus 1 over C2 to the power of minus 1 This is in series. In parallel for the capacitor, it will be C1 plus C2. For the resistor, the R equivalent is equal to R1 plus R2 if they are in series, and for the parallel, it will be 1 over R1 plus 1 over R2 plus 1 over R3 to the power of minus 1. Now the C equivalent for I number of capacitors should be written in this way. The equivalent capacitance of parallel combination equals to the sum of the individual capacitance. In parallel connection, the equivalent capacitance is always greater than any individual capacitance. In series, we found that the equivalent will give us always a smaller capacitance. The potential difference across each capacitor is the same in parallel combination. The charge on the individual capacitors add to give the total charge stored by the parallel combination. So let's practice now in some of the complex circuits. What is the equivalent capacitance of the following capacitors? Now we can notice that 1 and 3 are connected in series, so we use one of the shortcuts to find the equivalent capacitor or the equivalent capacitance here. I will use 1 times 3 over 1 plus 3, which is equal 3 over 4 farad. Also 4 and 2 are connected in series, so we multiply and we add, and it's equal to 4 over 3 farad. Now this will turn to this, and this will be turned to this. Now since this and this are connected in parallel, to find the equivalent we just add the capacitance of each one of them, so 3 over 4 plus 4 over 3, and the answer will be 25 over 12 farad. So C equivalent for this system is 25 over 12F. So in example 2 again, we need to find the equivalent capacitance. Notice that 2 farad and 2 farad is or are in parallel, so we just add them in normal way, and the equivalent will be 4 farad. Now 1 and 4 are connected in parallel, so we just add them. It is equal to 5 farad. Now this system becomes 4 and 5 FF. To find the equivalent, since they are connected in series, we just multiply and add. And the equivalent will be 20 over 9 farad. What is the equivalent capacitance of the following combination of the capacitors? We can notice that the 2 farad here are connected in series because we have one terminal in common, and we can find the equivalent of these two capacitors using one of the shortcuts. So since they are identical, then I will take the value of one of them and divide over the number of the identical capacitors. Since we have 2, so 2 over 2 equals 1. So here we have 1 farad, and here we have a 3. They are connected in parallel, so we just add them in normal way to get the equivalent. Now finally, this will be turned into 1 equals to 4 farad, and this one is 5 farad. 4 and 5 are connected in series, so we just multiply and add, and it's gonna be 20 over 9 farad. Now example 4, what is the equivalent capacitance of the following capacitors? 2 and 2 are connected in parallel, and we find the equivalent of them by just adding them in normal addition. Now the system becomes like this: 4, 3, and 2. Now here we have more than 2 capacitors, so we just use the reciprocal formula. I will use this one. C equivalent equals 1 over 4 plus 1 over 3 plus 1 over 2 to the power minus 1, and the answer is 12 over 13 farad. Example 5, what is the charge and the voltage of each of the capacitors in the following circuit? Now, let me remind you that whenever the capacitors are in parallel, then they will have the same voltage, but not necessarily the same amount of charge. And in series, they will have the same charge and not necessarily the same voltage. So the easiest way to find the voltage across and the charge across every single capacitor, it's recommended to use the C equivalent first. So let's turn this one into one singular capacitor. 2 and 1 are connected in parallel. We add them in normal way. And the equivalent capacitor of 1 and 2, let's denote C1 for the 2 farad and C2 for 1 farad and C3 equals to 6 farad. So C1 and 2 now equals to 2 farad. It is directly connected in series with the 6 farad. So C3 is equal 6 farad. Now we combine these two capacitors. They are connected in series. So I will use one of the shortcuts. I will multiply and add. So 2 and 1, it's a 3, not 2. So 3 here and a 3 there. And it becomes 2 farad. 2 farad is the C equivalent. Now this C equivalent is directly connected to the battery in parallel, which means the potential difference across the C equivalent is equal to 10 volt. Since we have the voltage and the capacitance, we can write that the Q for the C equivalent equals to the C equivalent multiplied by the voltage across the C equivalent. Now the capacitance is 2 and the V equivalent is 10. So the charge stored in this capacitor is 20 coulombs. Now if we go back, C equivalent is a result from the combination of C12 and C3, and they are connected in series. We know that whenever we connect two capacitors in series, they will carry the same amount of charge as well as the C equivalent. So we found that the C equivalent has 20 coulombs. So therefore the C3 and C12 will carry the same amount of charge. So Q of 12 equals to the charge in 3 equals to 20 coulomb. Now we need to find the potential difference here, which is exactly the potential difference across the C equivalent of 1 and 2. So the V of 1 of 2 equals the Q of N1 and 2 over the capacitance of 1 and 2. The Q in 1 and 2 is 20, so 20, and the capacitance in 1 and 2 is a 3, and it becomes 6.66 volt. Remember that the total is 10, and it will be divided across the two capacitors, the C equivalent as well as the 6 farad. So to find how much voltage will be here, it's enough to calculate it using the difference. So the V across the 6 farad or the C3, let's call it V3, equals to 10 minus 6.66, and it becomes 3.34 volt. Or you can simply calculate it using V3 is equal to Q3 over C3, and you will get the same result. Now, what about the charge in the 2 farad and the 1 farad? To find the charge in the 2 farad and the 1 farad, remember that the equivalent of these two capacitors will carry 20 coulomb, but it's not necessary will be the half here and the half there, because we have different amount of capacitance, and they don't carry the same amount of charge as the equivalent because they are connected in parallel. Remember, in parallel always the Q equals Q1 plus Q2. So the charge in the first capacitor plus the charge in the second capacitor will be equal to the charge in the equivalent of them. Now, since we know what is the potential difference here, And since these two capacitors are in parallel, then the voltage across the 1 farad and the 2 farad will be exactly 6.66. And it's equal to the voltage across the equivalent. So we know what is the voltage, we know the capacitance. Now we calculate the charge. So the charge across, this is C1, this is C2. So I will denote Q1 here. Q1 equals, so C times V, C1 and V1. Now C1 is given by 2 farad and the voltage is 6.6. So it becomes equals to 13.33 coulombs. Now remember that this capacitor will have amount of Q which is equal to Q1 plus Q2. Now we know that the total is 20. From the 20 we took for C1 amount of charge equals to 13.33, and the remaining amount will be stored in the Q2. So we can write that Q2 equals Q equivalent of the 1, 2 minus Q1. Q equivalent of the 1, 2 is 20, and the Q1 is equal to 13.33, 6.66 coulombs. What is the charge and the voltage of each of the capacitors in the following circuits? So I will use this space here to solve this question. Now first, let's find out the equivalent capacitor. I will denote this 1, 2, and this one is 3. So let's find out the C1, 2. Now C1, 2 are connected, 1 and 2 are connected in series, and we use one of the shortcuts to find the equivalent. I will use C over N, so 2 over 2 is equal to 1. Let's make a new sketch. Now the 1 farad, which is the C1, 2, is connected in parallel with C3, which is equal to 3 farad. And in parallel, we just add them in normal way to find the equivalent. So C equivalent 1 plus 3 equals 4 farad. So finally, we will get the sketch for this electric circuit, where here we have the C equivalent. Now the C equivalent here is connected in parallel with the battery. The battery has 10 volts. So the potential difference across this C equivalent is 10 volts. And the Q of the equivalent equals C equivalent times V equivalent. The C equivalent is 4, the voltage is 10, and the charge is 40 coulombs. Now this 40 coulombs is equal to the summation of the charges across this capacitor, or in this capacitor, and this in this capacitor, due to the fact that they are in parallel. So the charge in the equivalent of them equals to Q1 plus Q2, or Q12 plus Q3. Now, since they are connected in parallel, they will have the same potential difference, and this potential difference is equal to the potential difference across the C equivalent. The potential difference across 1, 2 equals to the potential difference across the 3, which is equal to 10 volts. Now, we know what is the potential difference across this one and that one, so we can now calculate the charge in each one of them. So Q3 equals C3 times V3. The C3 is given by 3, the V3 is given by 10, and the charge is 30 coulombs. Now the equivalent will store charge of 40. Part of this charge will go to the C3, and the remaining part will go to the C12. The charge in the C3 is 30, so the remaining will be 10 coulombs. So Q12 is 10 coulombs. Now, since the C12 is a result from the combination of 2 farad and 2 farad in series in the sketch, they are connected in series, so they will carry the same amount of charge as the one in the equivalent. So Q12 equals a Q of 1, which is equal Q of 2, which is equal to 10 coulombs. Now, finally, we need to know how much potential difference will be across the 2 farad here and the 2 farad here. Since they are equal or identical, the potential difference across each one of them is equal to the other. So the potential difference across the 2 farad is equal to the potential difference across the second 2 farad. We know that this set is connected in parallel with this set, and the potential difference here is 12 volt, and the potential difference here is 10 volt. So we can say that the potential difference across the C1 and C2, V1 equals V2, equals to 5 volt. So 5 volts here and 5 volt there. The total will be 10 volt. What is the charge on the 3 farad capacitor below? Now we can see that the 3 farad is directly connected with the battery using 2 terminals. So we have 2 terminals in common with the battery, which makes the 3 farad have the same potential difference as the battery. So we simply calculate it using Q is equal C3 V3, and the V here is the same as the battery. C3 is a 3, the battery is 5, and the charge is 15. Example 8, what is the voltage of the battery below? We can notice that the system consists of 4 capacitors. 2 are connected in series and 2 are connected in parallel. And the whole system is connected to a battery. Now, you know the voltage of the battery, it's enough to turn this system of capacitors into the equivalent, because we can find the voltage across the equivalent by writing the expression Q equivalent over the C equivalent. So I need to know what is the Q equivalent and the C equivalent, because the potential difference across the C equivalent is the same as the one in the battery. Let's start with this combination 1 and 3. Now 1 and 3 are connected in parallel, so let me turn it into one single capacitor. Now we just add them in normal way. This is 4 farad, this is 1 farad, and this is 2 farad. Now the 3C here, C stands for coulombs, and we know that coulombs is the unit of charge. Now, before we complete combining the capacitors, let me remind you that whenever we have capacitors in series, they will carry the same amount of charge. So this amount of charge tells me that the charge here is also 3 coulombs, and the charge here is also 3 coulombs, which means the charge on the equivalent capacitor will be also 3 coulombs, and this is the equivalent. So the charge is equal to 3 coulombs. Now we still need to find the equivalent capacitor, or the equivalent capacitance of this set of capacitors, and since they are connected in series, we have one terminal in common between the capacitors. Then to find the equivalent, we just find them using one of the shortcuts. So the C equivalent equals, I will use this one, 1 over 4 plus 1 over 1 plus 1 over 2 to the power of minus 1. And the C equivalent is 4 over 7 farad. Now we have the Q equivalent, we have the C equivalent. Let's find out the potential difference across the C equivalent, and the potential difference equals to 4 over 7 divided by 3. 3 here is the amount of charge across the equivalent capacitor, and the result is 4 over 21 volt. What is the charge on the 5 farad capacitor? So we start by simplifying this complex electric circuit into one singular one. So we know that the 4 farad and the 4 farad are connected in series. We will use one of the shortcuts to find the equivalent of the 4 and 4. I will use C over N. So 4 over the number of identical capacitors that are in series is 2. So 4 over 2 equals 2. And we can write simply 2 farad here, 1 farad here. Also, the 2 farad and 2 farad are identical and they're connected in series. So we use again one of the shortcuts, and the capacitance will be 1 farad. Now 5 and 3 are connected in parallel. To find the equivalent, we just add them in normal way, and 5 plus 3 is 8. Now, since this set is connected in parallel, we have two terminals in common. So we just add them in normal way, and 1 plus 1 plus 2 equals to 4. So 4 farad here, 8 farad here, connected across the 8-volt battery. Now remember, the 8 farad is related to this set, and I need the 8 farad to find how much charge will be holded in the 5 farad capacitor. Find the charge, you just need to know what is the potential with the capacitance. So I need the potential of the 5 farad and the capacitance. We already have the capacitance. We just need the potential difference across the 5 farad, which is equal to the same potential difference across the 8 farad. Because in parallel, the same potential difference will be across the set as well as the equivalent. Now let's combine 4 and 8 using one of the shortcuts because they are connected in series. So I will use 8 times 4 over 8 plus 4. So 24 over 11 is the equivalent capacitance. Now we know what is the capacitance of the equivalent. We know what is the potential difference across this capacitor. So we use this two information to find the Q equivalent. The Q equivalent is C times V. So 24 over 11 multiplied by 8. And it's going to be equal to 17.46 coulombs. This is the amount of the charge in the equivalent, which is equal to the same amount of charge of the individual capacitors that made up this equivalent. So this 17.46 actually is the same charge here and the same charge there. So now we know what is the amount of charge in this capacitor. Now we can find the potential difference across this capacitors, the 8 farad, which is essential to find the amount of charge in the 5 farad. So let's find out what is the potential difference here. So the potential difference across the 8 farad equals to the charge of the 8 farad and the capacitance of the 8 farad. The charge stored in the 8 farad is 17.46. The capacitance is 8. And the potential difference is 2.18 volt. Now this potential difference is across the 8 farad as well as across the 3 farad and the 5 farad. Now we have the potential difference of the 5 farad. Let's find the Q of the 5 farad, which is equal to C of the 5 farad multiplied by the voltage across the 5 farad. The C is 5 and the voltage 2.18. So the amount of charge is 10.9 coulombs. And this is the final answer. Now exercise 1. What is the equivalent capacitance of the set of capacitors shown in the figure? Now as we can see here, C2 and C3 are connected in parallel. So to find the C equivalent, we just add them in normal way. And we will get this result. 3 capacitors in series. We have C1, C4, and the equivalent of C2 and C3 actually is C2 plus C3. Now, since the 3 capacitors now are connected in series, we just use one of the shortcuts to find the equivalent of this set. And I will use 1 over C1 plus 1 over C2 plus C3 plus 1 over C4 to the power of minus 1. That means D is the correct answer. 3 identical capacitors with capacitance C are arranged as shown. What is the equivalent capacitance between points A and B? So we need to find the equivalent capacitance across A and B. We know that C and C are connected in series. So the equivalent of this set is, or this branch is C over 2. You can simply find it using C times C over C plus C. or you can use any other shortcut such as 1 over c plus 1 over c to the power minus 1. However, I will use this shortcut, c over n. We have two identical capacitors in series, so n equals 2, and the c represent the value of the individual capacitor, or the capacitance of the individual capacitor, and the capacitance is c. So you can write it as half of c. Now half of c is connected in parallel with c, which means we just add them in normal way. So half of c plus c equals 3 over 2 c. 3 over 2 c represent the equivalent capacitance across A and B, and the correct answer is C. 3 capacitors are connected in series as shown in figure 1. The capacitors are identical except the capacitor X has air between its plate, whereas capacitors Y and Z each have a dielectric slab of dielectric constant kappa greater than 1 between their plates. If the dielectric slab is removed from capacitor Z, this is the second trial, and in figure 2, which of the following describes what will happen to delta Vx, delta Vy, and delta Vz, the potential differences across capacitors X, Y, and Z respectively? Now, first of all, let me find the relationship between the capacitors or the capacitor filled with air and capacitor introduced with the dielectric. We know that according to the relationship that the C equals kappa C0, always whenever we have introduced a dielectric, this is the capacitance. After we introduce the dielectric, it's equal to kappa, the dielectric constant, times the capacitance when the same capacitor is filled with air or vacuum, which means we can say that for any capacitor with dielectric, it will be greater than its value when no dielectric is inserted within it. Now, also from the relationship C equals Q over V, we know that V and C are inversely proportionals, and also we can write it in this way. Since we are looking for V, I can write it as V equals Q over C. So when we introduce a dielectric, it means that the C will increase, and if the C increased, then the potential difference will decrease. Now, in the first trial, the potential difference across X is greater than the potential difference across Y and the potential difference across Z. And the reason for that is Y and Z have a dielectric slab, which means V equals Q over C. The C is higher now, which means the potential difference is less. However, for X, we have we have a capacitor with air filled, so the capacitance will be less with respect to the other capacitors, which makes the potential difference across X higher than the other capacitors, or higher than the potential difference across the other capacitors. Now, the constant in this two trials is the potential difference. Now, remember that the potential difference will distribute the voltage across the three capacitors. And for Vx, it will be the higher if you compare it with the other potential difference. Now, also here, after we have removed the slab, the potential difference will be divided across the components. But now Z will receive more potential because C now is less, which means the potential difference will be greater. But since we are dealing here with constant voltage, so the potential difference across Z will increase in a way such that the potential difference across X and Y will decrease. And that means that the potential difference across C is decrease, the potential difference across Y decrease, but the potential difference across Z will increase. Because the amount of increasing of the potential difference across Z does not come out from nowhere. So if you want to increase the potential difference here, it will be directly from the voltage. of the battery, which means the remaining voltage will be less than before to feed Y and Z. Now, when identical capacitors are placed in series with each other, what is the ratio of the equivalent capacitance of the series set to the capacitance of a single capacitor? Since we are dealing with identical, let's denote the capacitance of a single capacitor by C. Since we have n number of identical capacitor, then I will use the shortcut to find the equivalent. So it can be written as C over the number of the capacitors, which is in this case is n. Now here we need to find the ratio of this equivalent, this is the C equivalent, over the capacitance of the single capacitor. We have denoted the capacitance of the single capacitor as C. So we just need to divide the C equivalent over C to get the ratio. Now the C equivalent, we found it to be C over N. So it can be written as C over NC. C with C cancelled out, and the answer would be 1 over N. So the correct answer is C. Two parallel plate capacitors are connected in series as shown. Both capacitors have plates of area A and plate separation D. One of the capacitors is completely filled with a material of dielectric constant kappa. Which expression is equal to the equivalent capacitance of the two capacitors? So here the two capacitors are in series, but one of them is filled with a material of dielectric constant kappa. Now we know that for the capacitors, the C should be written as kappa times C0. Now the C0 is written as in terms of A and D in this way. So the C, after we insert the kappa epsilon 0 A times D, we just multiply by kappa. And by the way, this equation is given in the equations sheet. Now, since they are connected in series, so we just find their equivalent by using the multiplication over the addition. So we multiply C0 times C and we add them. C0 is epsilon 0 A over D multiplied by kappa epsilon 0 A over D over the addition. So epsilon 0 A over D plus kappa epsilon 0 A over D. Now from the denominator, we can take epsilon 0 A over D as a common factor. No need to do anything with the numerator because some elements will cancel out with the one in the denominator. So let's take the epsilon 0 AD as a common factor here. For the first term, we will end with 1. For the second term, only kappa will be there. Now we can cancel epsilon 0 A over D with epsilon 0 A over D. And then we can press this denominator down. So we can get that kappa epsilon 0 A over D times 1 plus kappa is the equivalent capacitance for this set. And it's found to be in A. So A is the correct answer. Capacitors C1 and C2 are connected as shown in the circuit above. The capacitance of C1 is C. The capacitance of C2 is C over 3. So one can say that the equivalent will be between A and B is we just add them in normal ways. So C plus C over 3, which is equals to 4 over 3 C. This is the equivalent. Now, a dielectric is inserted and it's denoted by CEQ. Now, a dielectric is inserted into capacitor C2. And the equivalent capacitance now becomes double the one that we found it in the previous trial. So after we insert the new or the dielectric material, the C2 will be promoted into kappa C over 3. So after we add it to combine and to get the equivalent, so C plus kappa C over 3, we can take the C as a common factor. So 1 plus kappa over 3. Now we found it to be double the one in the previous trial. So this actually is equal to double of the C equivalent. So 2 times 4 over 3C. Now C with C cancelled out. Let's solve it for K. So 1 plus K over, or kappa, over 3 equals 8 over 3. Now we multiply both sides times 3. 3 plus kappa equals 8. We move 3 to the other hand side, it becomes minus. So 8 minus 3 equals 5, and the correct answer is 5, which it's D. Now this is the last question for today's lesson. Each of the following figures shows 3 identical capacitors connected to a battery. Which arrangement has the greatest equivalent capacitance? Now remember that in series always we will get less capacitance than the individual, but in parallel we will get greater capacitance than the individual. So I will look for a circuit such that it contains the maximum number of capacitors in parallel, and actually it's found to be in E because all the capacitors are connected in parallel and there is no any series combination, which makes E is the correct answer. And that's it for today's lesson on 11.8 RC circuit part 1. Thank you for joining me. See you next time.